classic example is the shift from the geocentric to the heliocentric model of the solar system. If you have spent time observing the planets with a telescope, you know that the Earth's rotation is the primary motion you have to deal with through the night. The ancients, however, believed that the Earth was stationary. No, they did not believe it was flat, and the planets, moon and sun orbited around the Earth. This belief persisted partly because without telescopes, ancient people could not see evidence to the contrary. The main problem with the belief is that the planets occasionally appeared to wander backward against the fixed stars throughout the year. The word planet means wanderer in Greek. Nevertheless, the ancients devised solutions for this problem and maintained the paradigm until the early modern period, when telescopes caused it all to fall apart. Since then, other paradigm shifts have ushered in new eras of discovery. General relativity shifted our concepts of space and time from fixed to dynamic. Quantum mechanics questioned the underlying reality of measurements and the exactness of prediction. Each of these shifts occurred even in the absence of sufficient evidence to back up the associated belief system. The heliocentric model of Copernicus and Galileo was a poor predictor and needed Tycho Brahe's observations and Johannes Kepler's theories of orbits to establish. General relativity took decades because atomic clocks, lasers, radio astronomy, and other equipment were needed to corroborate its predictions. The shifts occurred not because the weight of the evidence demanded them, but because new theories resolved inconsistencies in earlier theories while explaining or predicting some new evidence that the older theories could not account for without clunky additions. The current great inconsistency now is how to formulate a consistent theory of quantum gravity. Unfortunately, while there are new theories, there are few solid predictions. We do not have a theory of quantum gravity that does for either gravity or quantum physics what Einstein's theory did for the perihelion precession of Mercury or the bending of starlight, nor what quantum theory did for blackbody radiation or the double-slit experiment. It is possible that scientific instruments are not sufficiently sensitive to usher in any new paradigm, but they one day will be. On the other hand, I argue that the main problem with current theories is that they all stick to the familiar paradigm of quantum mechanics while attempting to hammer the square peg of general relativity into the round hole of quantum field theory. After all, this is the program that worked for all other fields and the particles that belong to them. Some researchers recognize that general relativity, since it is a theory about space and time, the stage upon which all other forces and matter play, is different. Yet I think they struggle to work their way out of the old paradigms anyway. The old paradigms are roughly in lay terms these. Quantum theory is a mysterious and difficult to interpret property of reality that we get when we quantize classical theories such that measurements of particles are the sum total of many possible histories and influences from all space-time. In mathematical terms, this is the path integral. I could go on about other aspects like Wilson loops and S matrices, but the path integral is my main target. Space and time are manifestations of a four-dimensional manifold on which is defined a field called a metric tensor, which is the gravitational field. Matter and space-time interact via the Einstein field equations, which are derived from the Einstein-Hilbert action. Quantum gravity has suffered for decades because it is impossible to take the paradigm from two and apply one to it. There are fundamental problems with both the mathematical approach and the physical interpretation of such an approach. And most attempts to get around the problem involve changing two so that it fits into one. This is the basis of effective field theory, EFT, approaches to quantum gravity. Essentially, two is simply an EFT of some other theory. String theory, loop quantum gravity, causal dynamic triangulation, asymptotic safety, of which CDT is an example, or whatever else we can dream up as the small-scale representation of space and time. So far, this program has failed and has done so for about 40 years. The prevailing opinion of most of the proponents of these theories, however, is that without experimental data, we cannot know which one is correct, and therefore each should be judged based on theoretical merits. Meanwhile, researchers keep pushing each theory forward. I have no real problem with this. I've even praised more than one approach. On the other hand, my nagging feeling is that they are all falling into the same trap. The trap comes from sticking to the same old paradigm and assuming that quantum theory is fine as it is. After all, why mess with one of the most successful theories of all time? In particular, physicists have solved this problem before with other field theories like the weak force. Gravity is just more complicated. Yet this might be as pointless as trying to merge the Ptolemaic theory of celestial motion with Newton's laws. I think it is time for a shift in quantum theory as well, not because we have problems fitting gravity into it, but because quantum theory has its own internal inconsistencies. The main issue with quantum theory is the measurement problem. That is, quantum theory is incomplete because it does not include a theory or model for how predictions turn into measurements. Although there are numerous interpretations for how this occurs, I've made a video about Copenhagen, many worlds and so on ad nauseum, no evidence has supported any of them. Could this missing piece be the key to resolving quantum gravity? That is what I propose. Moreover, to find the solution, a paradigm shift must occur in which we think about reality, both the reality of measurement and that of space and time, quite differently. The funny thing about paradigm shifts, however, is that they appear at first glance to be ridiculous. The heliocentric model was ridiculed in its day. Surely the Earth does not move. Copernicus published his theory posthumously to avoid repercussions. Galileo was forced to recant the theory. Quantum theory was also ridiculed, as was general relativity. In fact, the Nobel Committee explicitly avoided offering Einstein a prize for relativity even after Eddington measured starlight bending in 1919, choosing instead to award it for the somewhat lesser discovery of the photoelectric effect. Thus, I expect any proposal I make to seem ridiculous. Nevertheless, here it goes. Fundamentally, I propose that quantum theory, or at least one interpretation of said theory, is correct. All matter, forces, and fields exist fundamentally as waves, including space and time. However, I propose that quantum theory is incorrect in its interpretation of how those waves behave. This is a roundabout way of saying I have another interpretation. Quantum theory suggests that waves in classical approximation are maximally constructive, but that this breaks down in the quantum realm. This is how we get interference between the wave representations of an electron with itself in a double-slit experiment. You can think of this in terms of water waves. If I make a wave in a still pool and it propagates to a distant barrier with two holes in it side by side, the plan wave on the surface will impact the barrier, and from the two holes on the other side will emerge two circular waves. These circular waves will then collide with one another and interfere to form a sort of crossing wave. Sometimes the peak of one wave will impact the peak of the other wave, and you get what is called constructive interference. And the peaks merge and become a larger peak. Sometimes the peak of one wave impacts the trough of another wave, and you get what is called destructive interference. They cancel out and you get a smaller wave or even nothing at all. If, in quantum theory, I were to assume all waves are maximally constructive, that would mean that a particle fired at a double slit would only obey a classical path going through one slit or the other. This contradicts what we observe. Imagine, however, a particle propagating in space and time. The particle, however, is also a wave. Thus, this particle is both a wave spread over space and propagating in time, as well as a point following a particular trajectory. Why we perceive these both, I will get to. A classical wave is constructed from all possible classical trajectories a particle could take. For example, a wave constructed from freely propagating trajectories conforms to a plane wave front propagating through space and time. If those are light particles, you get a single velocity, and the wavefront is very crisp, since you will get trajectories with different directions, but all the same speed. If they are massive particles, the wave will be smeared out, since it will be made of trajectories with different directions and speeds. If you have trajectories that follow curved paths, such as light rays flowing through an irregular medium, then you get irregular waves like these red lines, which correspond to the blue trajectories. Classical waves, however, are not the same as quantum waves because they only include classical trajectories. All the blue lines above are classical. The corresponding red lines thus only include classical trajectories. It is possible, however, to construct classical waves that are made up of both classical and quantum trajectories. Quantum trajectories for particles zigzag and don't necessarily follow shortest paths. With a modification to classical physics, however, we can represent these paths in classical equations. If we do that, we naturally obtain waves that look like the outcomes of quantum experiments, like the double-slit experiment. Although quantum mechanics represents particles as waves, quantum measurements do not detect waves. Instead, they detect particles alone. We only perceive the waves by inferring from where particles go after repeated experiments. It is difficult to explain this inconsistency in quantum physics, but we can. Now, in the past, I have conjectured that the fifth dimension explains what we observe in quantum theory because different classical outcomes occur at different slices of the fifth dimension. For example, in the case of Schrödinger's cat, half the outcomes along the fifth dimension are dead cats, and half are alive. There is some motivation for this interpretation, but I have always found it problematic. It makes the 5D theory a variant of the many worlds hypothesis and ushers in the deep philosophical problems associated with it. I have now gotten away from that idea by positing that particles are waves. Hence, there are no classical outcomes spread along the fifth dimension. Instead, there is a standing wave that does not change along that dimension. In fact, except in the case of gravity or fields in curved space-time, there is no way to infer that the fifth dimension is even there. I'm now conjecturing, I haven't proved this, that the key to solving the quantum measurement problem may not relate to the additional dimension at all, but to the principle of maximal constructive interference. Traditional quantum mechanics has no such principle. Rather, waves interfere in all kinds of ways, maximal and minimal. In a maximal interference formulation of quantum theory, whenever you place waves in superposition, the result is always maximally constructive. This means that if two waves interfere with one another, they are required to be in phase. Any slight modification to the phase of one to make it out of phase with the other is not allowed. Maximal constructive interference forces particles to obey the same rules that classically propagating particles follow. With a modification to their classical action, however, many more trajectories are allowed. All those in the quantum path integral, in fact. The particles are freed from the constraints of classical mechanics. This freeing of the particle reveals what has been lurking behind the curtain of classical mechanics all along. Waves govern the mechanics of particles. Unlike Bohmian mechanics, which has a guiding wave that steers a particle to its destination, one does not need a set of coupled equations. Bohm needed them both because he did not have maximal constructive interference. This principle allows the two to be merged into one equation for the wave, from which another can be derived via a constraint to get the particle. The Hamilton-Jacobi equation, its connection to geometric optics, and Hamilton's equations prove that we don't need separate equations. We only need to tweak the governing action to get a quantum action that is still the least. Because the wave is the fundamental propagating entity, it can represent all the dynamics of quantum experiments such as the double slit. Meanwhile, it is compatible with a single particle being measured thanks to the connection between Hamilton's equations for trajectories and its relationship with Hamilton-Jacobi for wavefronts. Thus, nothing happens at the moment of detection. The wave continues, as does the particle, decohering with the detector's own wave and particle nature. This also means that there is no such thing as unitarity. Or is there? While the Schrödinger equation and its equivalent Hamilton-Jacobi provide unitarity and indeed conserve probability flow, the actual particle trajectory, and indeed any aspect of the particle's state, comes by deriving Hamilton's equations from them under the assumption of maximal constructive interference. So it's not an either-or, but a both, and the wave and the particle are fundamentally a single entity, but the wave contains all the information and continues to propagate it forward while the particle carries specific trajectory information. This is true in both quantum and classical mechanics. This provides a mechanism for a Deutsch-Hayden interpretation of quantum mechanics in which the entirety of the wave mechanics are contained in local trajectory mechanics without wave collapse. This may, however, seem like a sleight of hand since I didn't provide a mechanism by which the wave and particle couple the way Bohm does. But that isn't necessary because the particle is how the wave manifests. Wave fronts and trajectories are duals of one another in both classical and quantum mechanics. This is perhaps the hardest aspect to grasp. So far so good, but now about quantum gravity. I further propose that this applies there as well. In essence, one can formulate the same equations for quantum gravity that one can for a single particle. They are more complex, being couched in tensor math, but essentially the same. Adding an additional dimension is necessary for the Hamilton-Jacobi approach, but by that, one avoids the problem of time since there is no difference between time and space in the equations. Then the neat trick is that having formulated the wave equations, we can derive the trajectory equations via maximal constructive interference in much the same way that Ulrich Gerlach did in his 1969 paper for classical general relativity, but using a quantum action. This approach requires a modification of both assumptions 1 and 2 in the current paradigm by reformulating 1 in terms of classical mechanics on a quantum action and adding a dimension to 2 to make it compatible. That is not a complete theory, since UV completion, for example, isn't yet addressed,